Have you ever really stopped to think about it? You tap a name on your phone, and in what feels like a blink of an eye, you're talking to someone on the other side of the world. It honestly feels like magic, but it's not. It's one of the most incredible, complex, and frankly brilliant systems humanity has ever built. So let's pull back the curtain on how it all works. What we're going to do here is trace the amazing journey of how we got here. We're going from the old days of clunky physical wires dedicated to a single call, all the way to the super flexible, software-driven virtual brains that run pretty much our entire connected world today. All right, so here's our game plan. We'll kick things off with the two big ideas on how to build a network. Then we'll dive into the secret language these networks use to communicate. After that, we'll see the game-changing moment when software took the driver's seat. We'll look at the ultimate system that runs everything now, and finally, we'll see how all this powerful tech actually connects right to your doorstep. Okay, so first things first. To understand anything about modern networks, you have to get your head around two totally different ways of thinking about moving information. This is the foundation for everything else.
So let's start with the classic way, circuit switching. This is how the old phone system worked. Imagine you want to talk to a friend. The network literally builds a private, dedicated train track just for your call. It's yours and only yours for the whole conversation. The quality is fantastic, guaranteed. But here's the catch. What about those moments when you're both silent? That entire expensive train track is just sitting there, completely empty, totally wasted, super inefficient.
Then came the internet, which just threw that whole idea out the window. It uses something called packet switching. With this, your voice is chopped up into thousands of tiny little digital pieces called packets. Each one gets a little address label, kind of like a car with a GPS. They all hop onto the public highway, weaving through traffic. They might even take different routes to avoid a jam. But they all arrive at the destination, where they're put back together in the right order. And wow, when you see them side by side, it's so clear why the world changed. Forget efficiency for a second, just look at resilience. With the old circuit switching, if your private train track gets a fault, poof, your call is gone, dropped. But with packet switching, if one road is blocked, the packets just find another way around it. That single idea, that resilience, plus the incredible efficiency is exactly why packet switching now runs everything. The internet, VoIP, 4G, and 5G, the whole shebang. Okay, so we've got all these packets flying around this massive digital highway. But how do they know where to go? How does the network manage all that traffic without it turning into total chaos? Well, it needed a nervous system, a hidden language to coordinate everything behind the scenes. For the traditional phone network, that brain was called the Signaling System Number 7, or SS7 for short. Now this is key. It's a completely separate network that works in the background. Before your call even connects, before you even hear a ring, little SS7 messages are zipping around the planet, setting things up. They're checking if the line is busy, figuring out the best route, and even grabbing the caller ID info to display on the screen. It's the hidden intelligence layer. And this SS7 brain, it's not just one thing. Think of it like a logistics company. You've got the SSPs, which are like the local post offices handling your mail. You've got the SCPs, which are these huge, centralized databases. They're the ones who know how to turn a 1-800 number into a real phone number. And then you have the STPs, which are the super fast routers, the delivery trucks making sure all those signaling messages get where they need to go, fast. The problem was SS7 was built for that old, slow, circuit-switched world. So when everything started moving to modern IP networks, we needed a bridge. And that bridge is called SIGTRAN. It's this really clever protocol that basically puts those old, reliable SS7 messages inside a modern IP packet, kind of like putting a letter in a high-speed pneumatic tube. It let us keep the old smart brain, but give it a brand new lightning-fast nervous system. And right there, that was the tipping point. This is where everything changes. Because once you have the signaling, the brain's instructions, running on the same network as the data, you can do something truly revolutionary. You can finally, completely separate the network's brain from its body. This is the birth of what we call the next generation network. The big idea here was just brilliant. You take all the intelligence, all the call routing rules and features, and you turn it into pure software. We call this a soft switch. And then you leave all the boring, heavy lifting, the actual moving of voice packets, to powerful but kind of dumb hardware called a media gateway. Think of it like this. The pilot, the soft switch, is now in a remote control center, and they can fly any airplane, any media gateway, anywhere in the world. This gave companies unbelievable flexibility and slashed costs. Now, these new software brains, they came in two main flavors. You've got the Class 4 Softwitch, which is just a monster. It's the wholesale carrier hub built to handle insane volumes of long-distance traffic between providers. Its only job is to route calls as fast and as cheap as possible. Then you have the Class 5. This is your local retail expert. It's the one that gives you your dial tone, your voicemail, call forwarding, all the features you actually interact with every day.
And this is so cool. You can see how all the pieces come together in a modern call. First, your phone sends out a request using a language called SIP. It hits your local Class 5 soft switch. That switch sees you're calling long distance, so it hands it off to a beefy Class 4. If needed, that Class 4 can even use SIGTRAN to talk to the old phone network. Then, the soft switches use a different protocol, H248, to tell the media gateways, okay, open up a channel. And only after all that setup happens does your actual voice, packed into little RTP packets, finally start to flow. But, even with all this progress, things were still kind of a mess. You had one system for mobile calls, another for landlines, another for data. It was just too complex. The industry needed a final destination, a single universal blueprint. One core to rule them all.
And that ultimate standard is the IP Multimedia Subsystem, or IMS. The best way to think about it is as the universal operating system for every kind of communication. It is the standardized framework that allows providers to deliver voice, video, and messaging services seamlessly over any network. Whether you're on 4G, 5G, or your home Wi-Fi, IMS is the magic that lets your phone call switch from the cellular network to your Wi-Fi without you even noticing. So this IMS core has a few critical players. When your phone wants to do anything, the very first place it knocks is the PCSCF. This is the network security guard, standing at the front door. It checks your ID, sets up a secure encrypted tunnel just for you, and basically protects the rest of the network from anything bad. Once you're past security, your request goes to the ICSCF. I want you to think of this as the network's directory assistance. It has one job and one job only: to quickly ask the main database, the HSS, hey, where is this person logged in right now? Which server is handling them? As soon as it gets that answer, it points your session in exactly the right direction. And that right direction leads to the SCSCF. This is it. This is the real brain of the operation, the conductor of the whole orchestra. It's the server that actually handles your registration, keeps track of your call from start to finish, and connects you to all the services you pay for, like voicemail. So you've got the security guard, the directory, and the conductor. This three-step process is what makes IMS so secure, scalable, and powerful. So we have this absolutely amazing, intelligent, unified core network. But how does it actually connect to the phone in your hand or the router in your living room? That's the final piece of this giant puzzle, the access network. For your home internet, the gold standard today is fiber optics. It starts in your provider's local office with a piece of gear called an OLT. A single strand of fiber runs from there out into your neighborhood. And here's the clever part. It hits a totally passive splitter. It's basically a glass prism that needs no electricity, and it splits that single beam of light into dozens of identical copies, one for each house. That light travels to a box on your house, the ONT, which simply turns the light back into an electrical signal for your Wi-Fi router. It's incredibly efficient. And there are two main flavors of this fiber tech you'll hear about. GPON is the big telecom standard. It's usually asymmetric, meaning your download is way faster than your upload, which is great for streaming video and TV. Then there's EPON, which is built on familiar Ethernet technology. It's often simpler and cheaper, and it's great at providing symmetric speeds, where your upload is just as blazing fast as your download. And what about on the wireless side? Well, there's this fantastic technology called Hotspot 2.0, also known as Passpoint. You've experienced this. It's that magic when you walk into an airport or a coffee shop and your phone just connects to the Wi-Fi automatically and securely. You don't have to find the network name. You don't have to type in a password. Your phone uses the credentials from its SIM card to prove who you are, making public Wi-Fi as seamless and as safe as using 5G. So look how far we've come. We went from dedicated copper wires for every single phone call to a global software-defined system that combines all our communication, voice, video, data into a single intelligent stream of packets. The network isn't just a bunch of dumb pipes anymore. It's an intelligent, programmable platform. And that leaves us with one last big question to think about. What happens next? What happens when this network stops being just a collection of connected devices and starts acting like one single, massive global computer?